equivariance of MLE, in other words, Fisher information, and 95% CI of MLE. There won't be a sufficiency question on quiz 2. So last time, and the last couple times in fact, we've seen that ML estimators have good properties. It's equivariance, consistency, and that ML estimators are asymptotically unbiased, normal, and efficient, where the variance achieves the Cramer-Rao lower bound. So these are all good things. And today we're going to talk about the mean square error of an estimator, and also begin to talk about the sufficiency of a statistic. So mean square error of an estimator. So the mean square error is used to measure how good an estimator theta hat is. So by definition, it's the expectation of the average distance between the estimator and its value and its true value. So we can write this as a multiple integral of this difference squared times the joint density, which factorizes. So the picture is basically you have the distribution of theta hat. This is a random variable. You have the true value, which may not be in the center of your histogram there, and we're looking for basically the average distance squared of theta hat from theta. So luckily, by this theorem, we don't need to do this yucky integral. The MSE is the variance plus the bias squared, where the bias is the expectation of theta hat minus theta. And so to prove this, the MSE is, we can write the inside of the expectation by subtracting and adding the expectation of theta hat. We then FOIL, and then you complete this proof for homework. Good job. So the picture of, we have basically a bias variance trade-off here, where you can have the same MSE. You can have two random variables with the same SE, one with high variance, low bias. That's the first picture here. So the first picture here is centered at theta, but it's quite spread out. Or you can have low variance, high bias. So here the variance is quite small, but it's focusing on the wrong theta. So as an example, let's look at x1, xn, IID Bernoulli. Remember the expectation of x here is theta and variance is theta 1 minus theta. So we're going to look at two estimators, sample mean and just the first component. So you can see that both of these estimators are unbiased, and their variances are theta 1 minus theta over n and theta times 1 minus theta. So clearly the MSE of theta twiddle is less than or equal to the MSE of theta hat. So our conclusion is that among all unbiased estimators, the MLE, for large sample size, has the smallest possible MSE since it is efficient, i.e. it achieves the Cramer-Rao lower bound. So as far as unbiased estimators are concerned, the MLE is the bomb. Now, however, note that the Cramer-Rao inequality only applies to unbiased estimators, and if you allow the estimator to be biased, you might get an even smaller MSE than what you find among unbiased estimators. So for many MSE is what is the best measure of how good an estimator is, and they'll relinquish unbiasedness if it means that they can have a smaller MSE. So the next topic we're going to do is sufficiency. So there are two primary motivations for sufficient estimators. One, once you collect your data, you can form a sufficient statistic and then throw away your data. You only need the sufficient statistic to estimate theta. So, right, when we're doing parameter estimation, we have all those trajectories, remember, to get the Fisher information, and to locate the maximum value of the likelihood, the theta that maximizes the likelihood. Well, imagine that you didn't actually need all of your data to do that. Maybe you just need a small subset of your data to do that. Well, that's where a sufficient statistic comes in. A sufficient statistic is basically a partition of your data set where a representative of each partition is sufficient to determine the estimate. So basically, this is important because in today, where we have huge data sets that are really painful to work with, we can collect that large data set and then keep just a small subset of it to determine the estimator. Secondly, you can make an estimator theta hat better, in other words, with a lower MSE, by taking the conditional expectation with respect to a sufficient statistic. So when we take the conditional expectation of theta hat with respect to t, or given t, this is a function of t. So I should say given here. Given a sufficient statistic t, right? This is a function of t now. And so the result of Ryle-Blackwell theorem is that this estimator is going to have a smaller MSE. We'll talk about this next time. But we need to understand what sufficiency means. So a statistic is a function of your data only. So for example, the sample mean, or the third component of your data, the minimum or the ordered statistic. But for example, the mean minus mu is not a statistic since it involves the parameter mu. Now, a sufficient statistic for theta, t is a sufficient statistic for theta if the conditional distribution of x1 to xn condition on t doesn't depend on theta anymore. So somehow conditioning on t removes dependence on theta. So in terms of densities, that's to say that the conditional with t, given t, when we condition on t being there, that is the same as if we just remove theta. Theta is not relevant anymore once we condition on t. So to understand this better, let's recall Bayes' rule. So Bayes' rule says the probability of A conditioned on B is the probability of A and B divided by the probability of B. So for densities, it says that, so let's say I always want to condition on theta, because theta is going to be some parameter. So so it says that I'm going to have the joint distribution including t, divided by the density of t condition on theta. And so, for example, let's say that I have x1 and x2 IID Bernoulli theta. So then the joint, which is the, so I should mention here that since t is dependent on x1 to xn, this is the same as just x1 is x1 to xn is xn. You don't need the t. That's redundant because if you know what all your x's are, then you would know what t is. Right? I'm assuming that the sum of x1 to x little n is t here. Otherwise, it would be 0, of course. So here's an example. F x1, x2, given theta. Remember, the formula for this is as shown here, highlighted. Now, if t is x1 plus x2, then ft given theta. So this is the probability that I have x1 plus x2 equals t given theta, which is basically the sum of all joint probabilities x1 and x2 such that x1 plus x2 is t. So here's a table. This is the sample, the outcome space for this joint has just 4 elements in it, because x is either 0 or 1. So then t, which is x1 plus x2, has 3 possible values, 0, 1, and 2. And then we've computed all of the conditional densities here, condition on t. And so, for example, condition on t where t is 0, we get so it's 1 minus theta times 1 minus theta in the numerator, right? Because x1 and x2 are both 0. And in the denominator, so it's all, right, it's all x, it's the probability of x1, x2 such that x1 plus x2 is 0. So the only way that x1 plus x2 can be 0 is for x1 to be 0 and x2 to be 0. So the denominator is also 1 minus theta, 1 minus theta. So you just get 1. When t is 1, now the denominator, for t to be 1, you can have x1 to be 0 and x2 to be 1, or you could have x1 to be 1 and x2 to be 0. So we have 2 terms, and so now that ratio is a half. So the point is that it's not dependent on theta. So what we're getting in the third column are numbers that are not dependent on theta. That's the big point here. Here's another example. So x1 to xn are IID Poisson theta. So then the numerator of the conditional distribution involving t is going to be this highlighted equation here, and the denominator is going to be this one, because if t is x1 plus x2 up to xn, that is Poisson n theta, so it'll have this formula. And then the ratio is going to be this, and notice that here this and this cancel, and this and this cancel. So we get something without a theta in it. Hence, t, the sum of x1 to xn, is a sufficient statistic. Okay, guys, have a great long weekend, and I'll see you next week.